Welcome. My name is Pla-Junca, and this is my project presentation for the course CES 5587, Topics in Wind Engineering. I selected the option of literature review, and the topic is performance-based wind design of cable-supported bridges. The presentation is structured as shown on the screen. I'll start with an introduction to performance-based engineering. I will follow with details on performance-based design in civil engineering, and I will end with conclusions and final remarks. So performance-based engineering is an analysis methodology that allows the designer to determine and know the performance of the structure under the design loads. So conventional code-based design approaches currently in place do not provide this information. So we design structures that we know are going to perform safely and adequately from a serviceability perspective, but we do not know the actual behavior of the structure under design loads. So performance-based engineering provides this information and also allows the designer to incorporate explicitly probabilistic uncertainty and explicitly quantify risk of failure. Performance-based engineering originated in the field of earthquake engineering through the Pacific Earthquake Engineering Research Center, or PEER. They developed a framework for the analysis that consisted of, on one hand, a hazard demand damage loss chain, and on the other, a list of performance objectives and corresponding acceptance criteria. So I will describe in a little bit more detail in the next slide these two features of the framework. And essentially this framework, what provides is a lot more insight on the structure under the analysis or design, which essentially enables a more informed decision-making by owners and stakeholders. So if we jump into details regarding performance-based design in civil engineering, let's start with performance-based seismic design. Performance-based seismic design has been implemented in the industry already, as opposed to performance-based wind design, which will be described later on, which has not been implemented in the industry yet. What you see on the screen is essentially a developed description of the chain that I introduced in the previous slide. It has 4 modules: the hazard analysis module, the structural analysis module, the damage analysis module, and the loss analysis module. They are all 4 related through a probabilistic relationship that is based on conditional probabilities, as you can see on the screen. So this relationship between the 4 analysis modules allows for the development of bridge-related curves. So on top of this, what we have is a list of performance levels and corresponding acceptance criteria. Think of performance levels as being, for example, your limit states in the current design code. So all together enables a risk-consistent evaluation of structural and economic performance, improved transparency in seismic performance evaluation, and clarifies trade-offs among safety, expected losses, and construction cost. If we switch to performance-based wind design, which again has not been implemented in the industry, the core probabilistic logic of it is the same as that of performance-based seismic design. However, the nature of the 2 hazards is very different, starting from their duration, frequency ranges, and other characteristics. And also, in the case of the wind engineering discipline, there's the presence of the exchange zone, which is a region where the wind field and the structural response are strongly correlated. So the presence of this exchange zone requires the addition of an additional module on the chain previously described for a performance-based seismic design that captures this interaction between the wind field and the structure. We identify it as the aerodynamic analysis module or interaction module, and is characterized by interaction parameters or aerodynamic and aeroelastic parameters. But again, the main probabilistic structure remains the same. It's modular, and it is based on conditional probabilities. Now, there was a major milestone in the future implementation of performance-based wind design in the industry in 2019 with the publication of the ASC pre-standard for performance-based wind design. This pre-standard is applicable to tall buildings. There's no such pre-standard yet for bridges or wind-sensitive bridges, such as cable-supported bridges. So in the field of cable-supported bridges, where we stand, so the current design practice is actually partially performance-based. Its cornerstone is wind tunnel testing, which is used to evaluate comfort, strength, and stability performances. However, overall, there's a lack of a comprehensive framework for full performance-based wind design. So currently, it's considered prescriptive, not performance-based. Now, where we stand in terms of performance-based design of this type of bridges. So the ASC Committee for Cable-Supported Bridges is currently developing a framework for performance-based wind design of this type of bridges. And eventually, we'll develop and publish a pre-standard similar to the pre-standard that the ASC has published for tall buildings. Now, at this point where the performance-based wind design of structures is being developed, it is important to also in parallel, develop a multi-hazard framework that enables the consideration of both hazard altogether for structures in locations where the two hazards coexist. This is important because the two hazards have competing performance requirements. So on one hand, for seismic performance, you need ductility. On the other hand, for wind performance, you need stiffness. So as you can see, the two are competing performance requirements. Such common framework will essentially allow for true optimization of structures designs. Now, some details. One fundamental question in wind engineering that now is being trying to be answered through performance-based engineering approaches is whether or not the structure can undergo inelastic behavior under extreme wind events. Currently, this is not allowed, but if it would be allowed, it would facilitate the optimization of structures that see the two hazards, the wind hazard and the seismic hazard. Currently, there's been research undergoing that is trying to answer this question. There is also research undergoing that's trying to establish this multi-hazard framework for structures located in locations seeing the two hazards. And this is where we stand at this moment in terms of performance-based wind design. So conclusions and final remarks. The industry is moving toward a unified risk-consistent design philosophy for wind-sensitive bridges through performance-based engineering. And performance-based wind design and multi-hazard methodologies have the potential to greatly enhance transparency, resilience, and efficiency in bridge engineering that will enable informed decision-making for owners and stakeholders. This concludes my presentation. Thank you very much for your attention. And I will conclude now.